last part is stereoscopic imaging. And what is stereoscopic imaging? There is a what shall I say, a misunderstanding in scanning electron microscopy, and that is that when you scan an image, we can go here. So here we have some stuff. If we scan this, how does it look like? All right, so I mean this is like a, let's say, this represent a typical electron microscopy image, scanning electron microscope image. And it looks like three-dimensional-ish. It's like a photo, actually. I mean, since it is a photo, it cannot be 3D. When we say 3D image, we mean that we have three-dimensional data. That is a three-dimensional matrix of data, x, y, z coordinates of the data points. This is just a two-dimensional data matrix. Yeah. So if we want to do 3D imaging, I mean, you need to use a machine that can produce real 3D data. Mm-hmm. And one such machine is like a confocal laser microscope that can do that. The Raman microscope we have also is a confocal microscope and can produce 3D data of the Raman signal. Here, since this machine is not really a 3D capable device, we cannot do 3D imaging. Okay. But what we can do is we can indirectly create 3D images by doing something called stereoscopic imaging. Mm-hmm. And that is when you look in a stereoscopic microscope, like the one over there in the Miller, or you have two oculars you look through, and when you look, you get a what shall I say, depth experience. Yeah. You can actually see how it looks like three-dimensional, because you have one light part to the right eye and one other light part to the left eye. So you get that kind of parallax vision. We can do that here also by taking several images and tilting them. Mm-hmm. And then we can put them in a software and recompute to calculate that parallax change. And so, what shall I say, indirectly process that data to generate a real 3D image. That we can do. And this is the similar thing as the discussion I had about the EDS, that when you're measuring with EDS, you get the intensity of the X-ray, and then you use as a model to get the weight percent. Mm-hmm. So this means that it is not, what should I say, the real original data. It has been processed through a model, so it can have glitches in it. Yeah. And same thing here in the stereoscopic. We process the two images or three images and create a 3D data set. Mm-hmm. And depending on how we do that, we can get more and less issues with it. So if you want to have accurate 3D data, then you would like to preferably use a machine that gives you 3D data directly, not indirectly like this. Mm-hmm. A profilometer, for example, or AFM. It's other tools that give you that 3D data. Mm-hmm. But here, we have an image scan. You can take over the controls. I'm so eager to do this. You're the student here. So, to do stereoscopic imaging, what we need to do is we need to take three images. Mm-hmm. One can do two also, but preferably you do three. One at the flat 0 degree tilt, and then two images with a few degrees tilted left, a few degrees tilted right. Mm-hmm. And one thing to note here is that if you take the stage over here, there is a tilt angle 0. Yeah. And now we are on working distance 7 here, so it's important to note that when you tilt the stage so you don't crash, right? Yeah. So how many degrees do we want to tilt? That depends on how big the obstacles are on your... so everything is about geometry here. Mm-hmm. It depends on the working distance and how big the obstacles are, how much you need to tilt. And usually the tilt angles is a few degrees, 1 to 5 degrees, or that is the normal range. And on this machine it is nice, if you look, that is the tilt manual control. If you click on that, you can hold the mouse there and then you can look and see what's happening. Okay, then that is the real image, that is the saved image. You see it tilts in the vertical direction, right?
Yeah.
So most electron microscope, they tend to tilt horizontally, but this machine tilts vertically.
Okay.
That's usually not a problem, but we need to remember that for the later when we're going to computate these images. So when you tilted it, we saw that it moved.
Yeah.
Why does it move? The reason why it's moving is if I have, let's say that this is our sample stage, and then our area we're viewing is over here. And when we're tilting, the rotating axis of the machine is of course fixed. You cannot move the axis of rotation. So if the sample is over here and you're tilting, you see it will translate in this direction. So that's why it moves. So the best way is to position your sample in the center, then the tilting will be more centralized. And that we have already done here. So this sample is already in the center of the carousel. But since in microscope everything is zoomed in, it will still move. Right? So a way to prevent that, if you put this back to 0, and then we put this in the view. Here it says keep view field is marked. There. So if you make sure that that thing is clicked, if we right angle here, let's say right -3 degrees, then it calculates, so what shall I say, the artificial axis of rotation. So it matches the view field. So now you see it's still in the view.
Yeah.
And we would like that, the object we want to study, we would like to have like that. So let's save a new image here now.
Okay.
And you can do this stereoscopic imaging on whichever detector you like and so on. That is less so concerned. Backscatter can actually be better. We can perhaps try that later, we'll see. You can call this -3 degrees, because we did -3.
Okay.
Yeah.
Close this?
Yeah, you can close that one. And then you can do a +3 degrees tilt. And then you save that image. All right. And then we can open the software that do the 3D imaging, and that is this it's called MAX. Mix, actually, not Max. I think you just click OK.
I thought it looked like a uTorrent.
All right, you can make a new folder here. I think, call it something. And you can go into that folder. Everybody tends to call them test, I think. And then we want to create a new data set in there. So I think you right click on the folder, if I remember correctly, and choose new project. There, and you right click on that folder also, I think. And here you, in new. Here we choose create dataset. So here it says, do we want to do 2 imaging or we do 3 imaging? We have made 3 images, so it chooses that one. And then you load up images here.
Let's see.
My folder right there. Yeah, exactly. There. Did you save it in here? Or? Yeah, there it is.
Yeah. Okay.
So it was
so
that was
one?
that was the center, but you clicked on the left one. So here it is. Shall I choose minus degrees or plus degrees on the left? We can try the plus.
Okay.
So the thing that will happen is that your image will be upside down if you do it in the wrong way, so to say. But the important thing to remember here is that this program thinks the rotation is horizontally. So that means we need to rotate each image.
Okay.
And there is a function for that here somewhere. There. No, not there is the rotation. So now it's rotated so the tilting is in the right direction for the program. And you can just click next now. You see it's less than small angles. Usually you want high tilt angles, but as I say, it depends on the sample. So we can just continue. So technically you need to do some trial and error here. What settings works for your particular sample. So then we come to this place here. So what we want to do now, if we look on the left image, we see there's actually two images. And we want to match them up. So you can, if there's a small image size, like you have in this case 2000 pixels, I think you can just hold down the mouse key and drag it. You see, it's a little bit slow. So if you release the mouse there, I usually use the numbers here and the arrows. So you see it. It's choose minus 36 is come closer, so try minus 70.
Okay.
So here, now you can see that this one matches. But if I go over the image, you can see that over here, it less match.
Yeah.
And that is because of this parallax thing. That is the thing the computer will use to generate the image. So, but what we want to do is that we want to match the same object in both images, and the thing that should be matched should be the object, the central object of interest. Now we took the particle on the side. So it's let's say that it's this big feature here that is of interest.
Yeah.
So then we would like to match actually over here.
Okay.
So if I click here, we can see that there is a little bit change here. And the higher tilt angle we have, of course, the more severe this will be. So smaller features need higher tilt. And then we do the same thing on the right image, but we can guess on the coordinates that it should be pretty similar, but in the opposite direction. So plus 89 here.
Okay.
You see, it comes pretty close.
Yeah.
All right, so now both objects has been aligned. Click next, next. So this, the final data image can only be in the green area now, because due to the tilting, something will be cropped up on the edges.
Okay.
So let's say we want the feature here in the center here now. We can take all this. Then it will calculate the image for us.
Okay.
So here, when we see the final image, now this was 2000 pixels scans we had. And the data points we get in the final image will be much less. I will see when it shows, but I think it's like 4 or 5 times less, something like that. So if we want to have high resolution in the 3D image, we want to scan a lot of pixels also.
Yeah.
So some can try. I have run this, and then you take 8,000 by 8,000 pixels and things like that. But then it can take like an hour to calculate also. So that is like a side effect of this, that you lose resolution when you calculate the 3D. And then in the future, we will not need roads. didn't say that in this Back to the Future movie. What does it say? It says the angle is very small, so the data might be less reliable. So, but that's fine.
Mm. What would be a good angle?
It defaults to more than 5 degrees, but it depends on. I mean, sometimes there is no right and wrong. So sometimes it's wrong to have a large angle also. Mm-hmm. Here we see our sample, mm-hmm. and now you see that there is a hole here.
Okay.
But it is actually something pointing up. You see, it became upside down because you choose the positive angle on the left image.
Okay.
Then it becomes upside down. But it's the same data set. So it's you just flip it like this and everything is fine.
Okay.
So here we can see the 3D representation. And that is the stuff that was pointing up on the surface there. Mm-hmm. But you see there's a lot of... it's not so, what shall I say, detailed as the original image because we lose those pixels.
Yeah.
But this is a real 3D data set now. So what we can do now, if we can do, for example, a profile measurement. Mm-hmm. So here is the data set. Mm-hmm. We can put in a line here. And then we can see the height of it. So here's micrometers. So if we make we can do the profile here perhaps. So that is the thickness of the paper basically. Mm-hmm. So it's here we have 0. So can we put in some measurements here? I think there is tools to measure also, right? Here we have tools. Region from reference level. This is the reference level. One can choose some points here. And the height we want to measure up here. No, that's true. Take that one also. Apply. Then you see it makes some average lines there. Mm-hmm. And we can see the height here. What does it say? The distance is 224 micrometer. Okay. Which is expectable because the paper I think is 100 microns or something like that, and then we have the coatings also, and it's coated on both back and front side. So it's reached 220 microns. Seems reasonable, I would say. Okay. But now we can measure some thickness. We can't do that in SEM.
No.
So this is a 3D data set now. But let's go back to not this. We can go back to this data, and we need to choose the glasses, the stereo pair vision, and how do we generate it? Here, now, it is generated, and then we should have, there is should be a configuration. One can choose how much to pull them apart, so to say.
Mm-hmm. Hold down.
Oh no, look.
What did you do?
Look.
Oh, okay.
Yeah, it works with the keyboard at least. Now, do we see it now?
Yes, now I do.
So now we can see it. You see this like very big thing, and it's like a pitch down. Actually, do you know what this can actually be?
No.
You see there's like a hole, and then there is like almost like something has been penetrating in.
Was it when you untouched the electrode, or?
Yeah, that is the front of the tweezer. That has been pressing into the graphite, and then we see it folded up on so we scratch it down and compressed it. Mm-hmm. And the nice thing with this is that the viewers on this YouTube thing, they can use the fancy glasses and see the same thing as we see now.
Okay.
That's the cool thing with this.
Awesome.
This is a great tool because it allows you to get you some kind of, what shall I say, depth information, measure I mean, there's so many user cases. You have some print, you want to measure the thickness of the print or something. This is one way of doing it. It is an indirect measurement. I want to emphasize that. I mean, there are direct tools like confocal microscope, profilometers, AFM. But the nice thing is it's very easy to do this. And it's compared to AFM, this is a very large area. This was 3 millimeter.
Yeah.
So you can see large things in it. But I think that concludes this second part, advanced session stuff. We've done a lot of things. Now we did the 3D stuff. We did this image snapping and stitching, as we call it. We did the EDS particles combined with the stitching for statistical analysis. And then we have gone through in previous session, we talked a lot about detectors, voltages, low vacuum mode, the STEM detector we went through. Yeah, it's like the plus menu at the burger shop. I have trained more than 50 people on this machine. And I mean, usually we do 2 by 4 hour training session, half day plus another half day. And after some time, you get tired. It is actually, there's a lot of information that I push through in 4 hours.
Yeah.
It's like a freight train coming, and you are very, very tired after the session also, and so on. So it's not. Some operators I have trained, they sort of tends to pass on after 2 hours and fade off into some fog, or I don't know. They start to get, what shall I say, lose their mental performance. So it is tough. I mean, but it's a modern machine, and 2 by 4 hours is actually amazing to run the whole microscope yourself. And we have had no incidents, no major failure on the machine caused by the user. So obviously it works. So yeah.
All right, it's done.
All right, that's it. So end of the movie. And that's the last thing you will see of me now, right?
And then you'll disappear.
Then I will disappear.